everybody. Well, welcome to NASA's Jet Propulsion Laboratory here in Pasadena, California for our monthly public lecture and discussion, the Von Karman series. I'm Preston Dykes. So tonight we're going to talk about one of the most fundamental elements of space exploration. How do we communicate with the robots that we send to far-off destinations across the solar system? Tonight, our focus is deep space communications and the critical tool NASA uses for that task, which we call the Deep Space Network. We'll hear from two speakers tonight, and then we'll move on to discussion, and then we'll take your questions. And if you're watching live online, you can submit questions on YouTube and Twitter, and we'll be sure to work in a couple of those as well during the Q&A. And so, to start us off, our first speaker will give us an overview of what's involved in communicating with spacecraft that are millions and sometimes billions of miles away from Earth. Please welcome the Deputy Director of the Interplanetary Network Directorate here at JPL, Dr. Les Deutsch.
Thank you, Preston. So those of you who think about the DSN, or the Deep Space Network, when you think about us, what you typically think about are large antennas, like this one, or or let's try the keyboard, or that one. And we are somewhat about large antennas and about a lot of other things too. Here is one of our three complexes or sets of antennas that we have around the world. This one happens to be in Canberra, Australia. And you can see in this are two sizes of antennas. Most of the antennas in this photo, the ones that are toward the left, are 34-meter antennas. They're 34 meters in diameter. The one that's over to the right is a 70-meter antenna. And to give you an idea of how big a 70-meter antenna is, it's sort of like a football field on a big hinge. It's that big. Being the Deep Space Network means that we are automatically a global enterprise. And you can, a little bit of thought, you can prove this for yourself. So this is a view looking down on the North Pole of the Earth. We have three, let's see, does the pointer work? Yes, it does. Okay. We have three of these locations that have antennas like that. The photo I showed you was in Canberra. It sits over here in Australia. We have a complex near Madrid in Spain and one at Goldstone in the desert of California. And the idea is, as the Earth turns, which is not a soap opera here, if you are a spacecraft off in deep space, as the Earth turns, there's always one of these complexes that's in view of your spacecraft, which means that we could provide continuous communication with you if you need it, or we can provide communications with you when you need it at any particular time, as long as there's not a planet blocking your view of us, for instance. And this is true for anything that's beyond 30,000 or so kilometers. I also drew a geosynchronous orbit, which is at 40,000 kilometers. That's the orbit at which, if you have a spacecraft there, it seems to stay over one point on the Earth. And I am a mathematician. I'm neither a scientist nor an engineer. So I think in terms of equations all the time. There are a lot of factors that come into describing the performance of a communications link with deep space. And I've listed a bunch of them here. And luckily, I'm not going to talk about most of them. So don't worry about that. But I did want to point out just the complexity of things. There are a whole bunch of parameters that talk about how well the transmitting spacecraft works, if it's trying to send a message to the ground. There are a whole bunch of parameters that talk about how well the receiving antenna works. But there's also all this stuff behind the spacecraft, things that provide interference or noise in the environment that we have to work about. But the most important parameter in deep space communications is the distance between you and the spacecraft. That's what makes communications in deep space different than communications anywhere else on the surface of the Earth, for instance. And we can describe this pretty easily. And remember, I'm a mathematician, so here's an equation. Don't worry too much about it. If you take all those parameters from that previous chart, all the ones that are good, They lump together in this term that's at the top of this fraction, and all the ones that are bad, the noise and interference, on the bottom. We call this thing a signal-to-noise ratio, and we use this term a lot in the theory of communications. And it is a figure of merit. The bigger this number, the more bits per second we can get back from deep space, as an example. And that signal-noise ratio is some complex constant over the distance between the spacecraft and you squared. So that's what makes it hard, is that distance becomes high. And the cartoon here shows this. So I have a geosynchronous spacecraft orbiting the Earth in this picture. That's the kind of spacecraft that provides your television signals, for instance, and most other communications on the surface of the Earth that uses satellites. And I also have a spacecraft to Jupiter. And the differences of those d squared terms is large, and the table shows this. If we take that GEO satellite, that TV satellite, and say that has unit difficulty, then even taking a spacecraft as far away as the moon makes it 100 times more difficult to communicate. That means if you can get back, say, a megabit per second from that geosynchronous thing, you can only get back 100th of that, just 10 kilobits per second at the moon with the same system. Mars is even worse than Jupiter's, where Jupiter, for instance, if you can get 400 megabits per second back from that GEO satellite, if you move that same system to Jupiter, you get 1 bit per second. That's how much harder that problem is. And that's why, if you look at the history of the Deep Space Network, among other things, it's the history of building bigger and bigger antennas. When we started out, we had 26-meter antennas, which we would now consider small. We went to 34-meter antennas, and we still use a lot of those. We went to 64-meter antennas at each site. Oh, it worked that time. And our largest antennas now are 70 meters. And if we need more than that, we can array antennas together. We can electronically combine the signals coming out of several of these antennas, and the overall performance looks like an antenna that has the sum of the areas of the individual antennas. So there's that same signal-to-noise ratio. It's also equal to a constant over what we call the noise temperature, which is a description of all the random, horrible events that can come between you and getting your signal. And some of these can't be controlled. And when I showed that first chart with all those parameters on it, if you have a planet behind your spacecraft, that planet might be radiating radio signals just naturally in the band that you're trying to listen to. That's noise as far as you're concerned. You don't want to hear that. You want to hear your spacecraft. There's cosmic microwave background just in the universe, and it's always there in our system. Well, we can't do anything about those, but we focus on things we can do something about and try to make that t as small as we can. One of the things we do is we avoid human-made interference in our bands. We locate our stations in isolated locations, and we control the existence of any other transmitters in the area, so nobody else is transmitting in our band. And in fact, for the frequencies we use for deep space communications, we have guarantees from the International Telecommunications Union, which is part of the United Nations. It's something that all countries are signatories on, that they will not transmit in our bands anything other than deep space spacecraft communications. And that's a UN-protected thing. We also have the best low-noise amplifiers in the business. These are the things that detect the radio waves as they come into the antenna. We actually cool them down to very close to absolute zero to get the best performance, because that's a direct contributor to that T term. So our typical low-noise amplifier is only 12 degrees above absolute zero. But we do more. And you're staring at this saying, boy, this guy just has typos all over the place. But in fact, you probably also read this correctly as error-correcting codes. That's because English is an error-correcting code. These are ways of encoding information that you want to transmit so that you protect it from typos. And in deep space communications, typos are when noise comes and clobbers a bit and flips it from a 1 to a 0 or vice versa. And I can show you a very quick example of how these work by looking at this 7-4 Hamming code. Don't worry about the name. So we have a 3-circle Venn diagram, and we want to send 4 bits from our spacecraft. So we populate the intersections of the circles with the 4 bits of the message, in this case 1, 0, 1, 0. Then we do the encoding. We complete the Venn diagram by adding bits so that each circle now has an even number of 1s. This is something that's uniquely doable, depending on whatever your original 4 bits were. Now we transmit. And on the ground, we got a typo. So in this case, when we transmitted from the spacecraft to the ground, the 0 flipped to a 1 because we had some noise in the system and it was bad. But don't worry, we can identify that as an error because now we look at which circles have an odd number of 1s. And there's only one that has an odd number of 1s, and it's this one. And therefore, we know that all the bits that are bad are only in this circle. So it can't be an intersection with another circle. It's only this one, so that's got to be the bad bit. And in fact, just to show another example, if instead this bit had flipped, we would do the same decoding algorithm. We discovered that there were 2 circles that had an odd number of bits. And so the bit that's uniquely at the intersection of those 2 circles has to be the one that has the error. So this is very, very powerful. To give you an idea of how powerful this is, the kinds of codes that we use, which are not this simple, in the Deep Space Network, are so powerful that it's as if we had 10 times the communications performance. By using these codes, we can get the same bits per second down for 1/10 the power, or a smaller antenna, or something. And that's huge, because if we didn't have this, we'd have to have, for example, 10 times the number of DSN antennas to get the same overall performance. We also do a lot of data compression. We don't want to send anything from our spacecraft in deep space that we don't absolutely have to. And I like to think of data compression as something like texting. So here's a text message. And you all can read this, particularly if you have children at home. And what that says is, for your information, Joe will be right back to help later. But look at the difference in the length of those sentences. If you do the calculation, it's a compression ratio of 39 characters to 24. We only sent 24 of the original 39 characters, or actually it was a different set of 24. That's almost a factor of 2 to 1. We got by with sending only half the characters, and we got the entire content of the message understood on the ground. That's very powerful. It turns out that the images that we take with our spacecraft typically can be compressed 10 to 1. So there's another factor of 10, just like the coding. It's just as powerful. It turns out that if you have other kinds of data types that have even more redundancy in them, more structure, things like videos, because videos are subsequent frames of images, and so not only can the image be compressed, but they don't change much between frames, and that's important. Or hyperspectral images. These are images where each pixel is actually a spectrogram that tells you, for instance, what kind of material you're looking at on the surface of a planet or a moon. Those things could be compressed more than 10 to 1. And, oops, went a little too fast. There are other things we can do that even do better compression ratios. For instance, as we navigate our spacecraft in deep space, if we can do that without talking to the Earth and just send the answer, I'm going to be here tomorrow, that's a huge compression of what needs to be sent. We can also, for instance, take images but only send back the interesting parts of them. We've done this with missions. And we can, in the limit, we can answer some scientific questions on the spacecraft and only send the yes or no answer, as opposed to tons and tons of information. And we have research going on in all these areas at the moment. So how well have we done? Since we started doing communication with deep space in the late 50s, we have done phenomenally well. And what this chart shows is a little bit hard to understand, because what I've done is normalized everything by the distance squared. We've taken every point in this curve, which is represented by a particular spacecraft communicating with the Earth, but in our minds, we've moved that spacecraft to Jupiter. So they all have the same distance squared. So all that's left is everything else in those equations. How big are the antennas? How powerful are the transmitters? How efficient are the low noise amplifiers? How good are the codes and compression? And if you just look at this, for things that are under our control and distance isn't, we have improved communications by a factor of 10 to the 13th. Now that's a huge number. We had to report this to Congress a couple years ago. So we had to come up with a way for Congress to understand how big a number this was. What we ended up telling them was that if you took all the words in the Library of Congress and added them up from all the books that are there and all the magazines and so forth, twice you come up with 10 to the 13th. So we do more than communicate with our spacecraft. We also have to steer them. And this is an example of the Dawn spacecraft. It's coming to the end of its mission, but it launched from Earth. It had a Mars flyby, zoomed around a few times, and got to its pair of asteroids. We had to know where it was. We had to understand the direction it was going. And this is hard to do because there is no GPS in deep space. We can't do it this way. So what do? We actually do most of the navigation trying to understand where the spacecraft is and what direction it's going by looking at the radio signal. And there are three main things that we do. Some are easy to understand, some not as easy. Ranging. What we do is we send a signal to the spacecraft, and it immediately sends it back. We measure the time, and that gives us a measure of how far away the spacecraft is. That's an easy one. Doppler. Doppler is a change in frequency that's the result of relative motion between the transmitter and receiver. It's the same effect you have when a fire engine goes by you on the freeway. And you hear that drop of signal, as the drop of the frequency as it goes by. And we look at the Doppler, we measure the Doppler and the signal, the difference between the frequency we know that was transmitted and what we actually received. And that tells us something about the relative motion of the spacecraft and the DSN. And the third thing we do is something that's called delta differenced one-way ranging, or delta DOR. Don't worry about that. What it basically is using a pair of DSN antennas to triangulate, so have them both look at the spacecraft and very precisely measure the angle in that triangle. And that tells us something about, again, the distance, but also the distance relative to that baseline between the two antennas. These are the three main types of information we use to navigate our spacecraft. We also supplement this with sensors that are on board the spacecraft. For instance, if the spacecraft has a good camera on board and it can photograph, say, the asteroid to which it's going against the stellar background, it's sort of the same thing as how we navigated sailing ships in the age of exploration on Earth. And we can do the same thing in space. Last thing I want to talk about is the way we use the DSN as a science instrument directly. So if we have a spacecraft, in this case I'm showing Cassini, sitting above the ring plane in Saturn and transmitting its radio signal through the rings to the DSN. We measure various perturbations in that signal, changes relative to what it should have done if there weren't any objects or anything in the way. We look at the amplitude of the signal and see how it fluctuates as the signal traverses things. We look at wobble in the spacecraft, and we look at the frequency deviation. And this tells us a whole bunch of things about what is between the spacecraft and the DSN. This allows us to study rings and particles in the path. Most of what we know about Saturn's rings, including this particular image, are the direct results of DSN science, not photography. We study atmospheres of planets. Again, as the spacecraft, for instance, continues and goes behind Saturn, the beam actually goes through the atmosphere of Saturn. And as it glances, we can actually look at the beam traverse different altitudes in the atmosphere, so we can get a measure of the density versus altitude in the atmosphere. We learn about the interiors of bodies. And we do that by looking at how the gravity in some of these irregular bodies affects the motion of the spacecraft. This is how we know, for instance, if there's a liquid ocean under the surface of Europa. Not because we found it some other way, it's because we've done it with the DSN. We have our challenges. And that is, although d squared isn't going to change, the things that we send into space are getting better and better. The instruments are getting better and better. And we want to get more and more data back from them. And when we do sort of a market analysis of this every year, we look at 30 years into the future, and we try to forecast as best as we can what missions might fly in that time frame based on a constrained NASA budget, and what kinds of data rates they're going to want to get back from deep space. And what you see here is a family of curves. Each one represents a different scenario, different set of missions that might fly. But they all have this upward slope. And the upward slope is about a factor of 10 in bits per second per decade. That's how much better we have to get on that 10 to the 13th curve. Every 10 years, we have to go 10 to the 14th, 10 to the 15th, and so forth, just to keep up with where mission designers want to go. And one of the things we're going to be doing to help that is adding optical communications to the DSN, communicate with photons on laser beams. We're actually going to be demonstrating this in deep space for the first time on the Psyche mission, which goes to the metal asteroid Psyche in the main belt, launches in 2022. It will carry a deep space optical communications terminal on it. For this demonstration, we're going to use the Palomar 200-inch optical telescope, the astronomy telescope, as a receiver. But we won't be able to do that afterward. We'll have demonstrated the technology, but to do this operationally, we can't keep borrowing somebody's optical telescope. We have to do something else. So what we're going to do, as depicted in this image, is we're going to add spherical optical mirrors to the inner 8 meters of a 34-meter antenna. We've actually just started this project. We'll place a photon counting optical detector at the apex, which is this structure up here. So the light will come in, bounce off, go to the detector. And we'll actually use a separate, much smaller telescope to send information back to the spacecraft. So we'll have a two-way link, but using 2 different antennas. And with that, I think I'll end my talk. Thank you.
Yeah. All right, thanks, Les. Okay, well, as you heard from Les, NASA anticipates that our spacecraft are going to be sending an ever-increasing amount of data over the next several decades. And so that means one thing: we need more bandwidth. So our next speaker is going to tell you about an important part of how we're going to address that challenge. Please welcome the manager of the Deep Space Network's Aperture Enhancement Project, Amy Smith.
Thank you. Yes, so I'm going to talk to you, oops, wrong way. There we go. So I'm going to talk to you about the DSN Aperture Enhancement Project, which is one of the ways that we're going to deal with the ever-increasing demands on the DSN. So DSN Aperture Enhancement Project, or DAEP, as you'll hear me refer to it, is going to add capabilities to the DSN. We're going to construct new 34-meter beam waveguide antennas at all of our complexes. And at the end of the project, we will end up with 4 34-meter beam waveguide antennas at each complex, which not only gives us additional apertures, additional antennas that can be scheduled, but it also gives us the capability to array those 4 antennas, which will provide capability similar to the 70-meter antenna as a backup to that limited resource. So, DAEP started back in 2009 with the construction of 2 new antennas at the Canberra complex. Those 2 antennas were delivered in 2014 and 2016, and you can see some pretty pictures of our brand new antennas there. In 2016, we broke ground on the next set of antennas at the Madrid complex, and those are currently under construction, and I'm going to give you a little bit of a status update on those in a couple minutes. And then we've just kicked off the next antenna, which will be built at the Goldstone complex and delivered in 2024. And then the final antenna will be built at Canberra and delivered in 2026. So this is kind of a busy chart, but this talks about the rollout plan for the entire project. And so you can see each one of these boxes represents one of the complexes. And up at the top, you can see the beam waveguide antennas. And all the ones in the little boxes are the ones that we're developing and delivering now. So in addition to adding these antennas, you can see some more information up here shows that we're adding different frequencies. So we'll be adding additional frequencies to some of these antennas, and other ones will be delivered with higher power transmitters. And all of these things together help increase the capabilities of the network overall. So I keep talking about this 34-meter beam waveguide antenna. Let me tell you a little bit about what I'm talking about. So I like to start at the bottom. So down here at the bottom, we have the pedestal room. It's a concrete foundation in a room where we can house the microwave transmitter and receiver electronics. And then on top of that, we have a steel support structure that not only supports the reflector, but actually provides the motion in both the azimuth direction and in elevation. And then, of course, at the top, we have the 34-meter dish, which is why we call it 34 meters. It's a large dish, not quite as big as the 70-meter. But the way that this works is the large dish listens to space, and it hits the radio signal, and it focuses that energy up on the subreflector, which then in turn bounces it through a series of mirrors down into the pedestal where our electronics are. And one of the key things that makes the beam waveguide antenna different from some of the other designs is it takes all the electronics and the electronic feeds and puts them down here in a stationary room, which is much easier to maintain. You got room to upgrade things, and it takes them out of the tipping structure, so you don't have to design them to move with the rest of the antenna. So let's talk about Madrid. I'll talk about a little bit of the process of how we build these antennas. So the first thing we need to do is dig a big hole, because this pedestal room actually resides underground. So in Spain, we actually used explosives to blast out this big hole, and then we built a foundation. So that foundation is about 1 meter thick of concrete. You can see these are the people pouring the concrete this day. It actually took 50 trucks of concrete to fill just the foundation level, just the floor. So after you let that cure, you then build up the walls. The walls are just under 1 meter thick, but it takes 2 separate days pouring to achieve the walls at the proper height. And then once you do that, you pour a concrete roof. The roof is not quite as thick as the foundation, but it still took 31 trucks to pour the roof on this antenna. And you can see a person here for a height reference. Once you're done pouring all that concrete, we backfill the area, and then you can start building the antenna on top of it. So the first thing we do at that point is to put in the azimuth track. So this is what the antenna actually sits on and rotates around. And so this is a really precise installation. We need to make sure it's well aligned and perfectly smooth to allow for the motion we need on the antenna. And then we can start building up the actual structure, including the beam waveguide itself. So here we see the steel base frame structure and the waveguide itself going up, built up onto the pedestal. And at the same time, we start building the reflector structure. But the reflector is built up of a lot of steel parts. And so it doesn't make sense to build it on top. They build it on the side where they can put all those pieces together. They bolt it together, they weld it together, and then they bring in a very large crane and they lift it and install it on top. And actually, we are right now preparing for that first lift in Madrid, which is scheduled to happen next week. So we're busy measuring and doing the final preparations for that, which is very exciting. Because once it gets up there on top, that's when you can start installing the panels in the subreflector. You can start installing the electronics and all the facilities that's necessary to support these antennas and test it and bring it into operations. So there's lots of unique challenges in building new 34-meter antennas. It's kind of like building a multi-story building, right? It's a huge structure. It's got a big foundation. It's got to be analyzed to support the weight that's going on it. But in the end, it's not a building, it's an instrument with very stringent and precise requirements. So that adds a little bit of an interesting problem when you're talking about construction, because it's hard to make these things very precise. So there's all sorts of things that go into the design and then the assembly of these things on site to make sure that we can meet the stringent pointing requirements. That once it points at a spacecraft in deep space, that it can track it, it can follow it smoothly, and all of the motion continues to support the link, and you don't drop the link. In addition, there's specially designed electronics that Les talked about. Some of our low-nose amplifiers to receive these really weak signals. In addition to the cryo-cooled LNAs, the low-nose amplifiers, we also have ultra-stable frequency references. And then we have high-power transmitters. So for example, the DSN could transmit your cable signal all the way to the surface of Jupiter. Right, so this is a high power signal, and it comes with some infrastructure challenges. So we need to make sure to keep these high power transmitters cool. So we have specially designed HVAC and cooling systems that all have to get integrated. And then of course, once you've launched your spacecraft, you want to make sure you get all of the data. So everything has to be reliable. So to make sure that the links all the way through the antenna and all the way back through the data collection is very reliable. Okay, so I'm going to change gears really quick. Les mentioned the optical comm, and the next antenna I said we were developing out at Goldstone will actually be the first one to receive an optical terminal that we're developing. So right now we are in the prototype phase. So in the next couple years we'll be developing a part of that system, and we will be able to take it out to our test antenna at Goldstone and test it out, and then take the things we learn from that prototype development and apply it to the implementation phase. And we will we plan to have an operational optical system at Goldstone in 2025. And it's kind of an exciting way to do this because you can take advantage of all of the infrastructure that's already there. You've already got all of the foundation, the steel structure, all of the motion capabilities, even all of the facilities that are necessary for a new antenna. And so you can focus your efforts on really designing the technical capabilities of these mirrors and of the system, because you get to install it on an already designed, already existing antenna. So that's where we're going in the future, and very excited about it. So I'm going to leave you now with a little video. I talked a lot about the construction process of these antennas, and we have a nice time-lapse video of one of the antennas that was built in Canberra recently, and Les has put together a video which I'm going to show you right now, so you can see kind of how this really works and the complexities and the process of how this goes together.
All right. Thanks, Amy. If you didn't catch it at the start, the music in that video was actually performed by our first speaker, Les Deutsch. He actually has a post as the official organist at Caltech, so talented guy. Yeah. So while we're doing a little set change here, I want to talk to you a little bit about what you see on the screen throughout our show. This is what we like to call DSN Now. It's a real-time visualization of the activity on the Deep Space Network. So on the left over here, you see the 3 antenna complexes. Each one has its own row in Spain and California and Australia. And for whatever spacecraft we're talking to at any given time, you'll see some squiggly lines that represent data coming up and going down. and you can select any of the antennas you like, and on the right it will display more detailed information about the mission that we're talking to, including the strength of the signal, the data rate, even the wind speed at the antenna site. So it's a lot of really cool info, and it's run by the real data as it's happening. So it's available on any browser, including on mobile. So just search for DSN Now in your favorite search engine. Okay, so let's talk a little bit more about deep space communications. In addition to Les and Amy, we are joined by Mike Levesque. He serves as the manager. Hey, Mike, you serve as the manager for service management and operations for the DSN.
Yeah, that's
right?
correct.
So let's talk a bit about just how many spacecraft the DSN is tracking and communicating with. It's not just 5 or 6, is it?
No, in a course of a month, we'll track up to 40 spacecraft, depends on a monthly basis, but we have quite a few spacecraft. And they're really across NASA, so of course JPL spacecraft, our favorite, but all the agencies of NASA have spacecraft in deep space, as well as international partners, JAXA, European Space Agency, of course, India's Space Agency, Korea is going to send up a deep space probe. So, quite a group of spacecraft there.
Now, is the DSN the system that we use to communicate with the International Space Station and the satellites that are orbiting Earth studying the planet?
No, actually, although the DSN is extremely well designed and optimized to track spacecraft that are very far away, it has trouble with ones that are very, very close. And that's because, like the International Space Station, if you watch it come overhead, it goes pretty fast. And moving a 70-meter antenna at that speed is a very difficult thing to do and maintain the precision. So in fact, NASA has 3 communication networks. They're all managed out of the Space Communications and Navigation Office, SCAN, at NASA headquarters. The DSN, the Deep Space Network, is one of them. There are 2 others. There's something called the Near Earth Network, which is a set of very small antennas, typically between 5 and 12 meters. There's some 18-meter antennas in the mix that communicate with a lot of satellites in low Earth orbit. The International Space Station is one of the spacecraft that actually communicate upward. NASA has the 3rd network, which is called the Space Network, which is a set of relay spacecraft that sit at geosynchronous altitude. So they stay in a fixed place over the surface of the Earth, as we mentioned before. The ISS actually sends their radio waves upward and are received by those spacecraft and then relayed back to Earth. And there's always one of those in view as the ISS orbits, so they can get communication whenever they need it.
Well, so how do you, for the ones that you are talking to much farther out, how do you meet the needs of all these missions in terms of scheduling? I mean, I can imagine that every mission would like to have a hotline to Earth at any time that it wants it, but it's just not possible, right? I mean, how do you balance all of them?
Yeah, that's right. You can see we really only have 12 antennas, and of course we're building new ones and decommissioning old ones. And with those 40 spacecraft, there's quite a bit of competition for time. So, back in the old days, that was all done with paper cards on tables, negotiating every week about who's got what time slot, And then, thankfully somebody invented Post-its, so, you got to use Post-its, which helped a lot. But of course, today we use software, and we have some AI-assisted software that we can put in requirements of each of the spacecraft and develop temporal networks of that, and then construct the schedule from that. And then when there are conflicts, inevitably there are, we have some collaboration software that the schedulers can get together from the different missions and negotiate out who gets that time and make trades based on that. So it's quite an endeavor.
So an interesting part of that problem, if you look at DSN right now, there's not a lot of activity at Madrid. The activity is in Goldstone and Canberra. The reason for that is when people send spacecraft into deep space, it's not just uniformly populated across deep space. They tend to want to go to specific places. Mars is a place of interest. There's always a lot of spacecraft around Mars. spacecraft tend to go to places where there are other objects to study, for the most part, not unilaterally. But that means that they tend to clump in parts of the sky. And if you think of just going outside with your telescope and looking at planets, you know that sometimes there's only one planet that you can see, and sometimes there are four. When there are four, there's a lot more contention for the DSN.
And we're doing other things too in terms of scheduling. So Mars, there's quite a few spacecraft around Mars today. So we can actually point the antenna at Mars and communicate simultaneously with up to 4 spacecraft with one antenna because they're separated by frequencies. So, and generally we only have one uplink at a time, but that can switch between those spacecraft. So, and we call that multiple spacecraft per aperture, and it helps a lot. You can imagine talking to 4 spacecraft rather than one at a time.
And Amy, some of the new capabilities you talked about will help to meet that increasing need as well, right?
Yes, of course. So we'll have new apertures, which can be added to the schedule. And so we'll have an easier job on some of the scheduling trouble. But it's kind of interesting, actually. The order of construction of the DAUP antennas was designed specifically to meet the needs of spacecraft. Like Les was saying, they're clustered in certain places, which means that at the beginning of DAUP, there was a need for additional apertures down at Canberra in the southern hemisphere. And right now, the Madrid antennas are being built to support the next set of missions that are going to Mars in the 2020 timeframe.
Well, so there are these 3 DSN sites around the globe in an array, but you guys all work for the American space program. So how do you work this collaboration and coordination with all the other countries that are involved in this global enterprise?
Yeah. So we mentioned before, I think Mike mentioned that we track not just NASA spacecraft, but spacecraft from a lot of other countries. And in fact, some of those other countries also have deep space network-like capabilities. The European Space Agency has a similar thing to the Deep Space Network now, although there's only one antenna at each of 3 locations around the world. Basically, what we have done is we've worked with all the space agencies of the world and created a set of standards for communications so that their spacecraft can talk to our antennas and our spacecraft can talk to their antennas. They all speak a similar data system language, and that allows us to do this cooperative tracking.
And these they're super capable and they're gigantic, but they're also really precise, high precision instruments, right? And Amy, so can you talk a little bit about some of the ways that these things are very precisely engineered and designed?
Yeah, so I talked a lot about the structure and the construction of antennas, but I didn't talk too much about the reflector itself. So the reflector is actually made up of a whole bunch of panels. We have 9 rows of panels that are very carefully designed and built. So they are built with a surface to 5/1000ths of an inch. That's the thickness of 1 or 2 sheets of paper. And so they have to meet that surface tolerance. They all have to be built to that surface tolerance, and then we install them on the antenna. And then actually, once we install them on the antenna, they're all adjustable. So we go in and do calibration and measurements to set these panels exactly the way we want them to make sure that we have maximized the gain available to us. So we have a dual shape system in which we can really set this up to maximize the gain for each of these antennas.
I was going to actually
You
add a
define
little.
gain real quick, either one of you?
Sorry. That's the power in a direction, right?
Yeah. So I wanted to just add to that. It turns out that the higher the frequencies that you're communicating with, the harder it is to point the antennas. And it's saying a lot that these antennas that were originally designed to operate at maybe 2 gigahertz are operating routinely at 32 gigahertz today. But what really surprised me was when we did the feasibility studies for adding optical dishes to these 34-meter antennas. It turns out that the pointing system is stable enough even for optical frequencies, which is really saying a lot about the precision in the design.
Wow. So speaking of pointing, then, how do you guys manage the passing of the baton, so to speak, from antenna complex to complex? Because you've got a spacecraft up in the sky, maybe it's a Jupiter, and so you're tracking Jupiter, but Jupiter is going to eventually set, and you can't see it anymore. So how do you hand it off to the next
We call it handoff, in fact. And so from complex to complex, we do handoffs, and that's both uplink and the downlink. And so you can't uplink at the same time to that spacecraft, so we kind of precisely time shutting off an uplink at one site and activating the uplink at the next site. And of course, you may have some little glitches in that. Usually we're able to overcome that and have a continuous transmission both on the uplink and the downlink side, even during these handovers. And we're actually handing over for other agencies too. So we're not the only deep space network. There are other sites around the globe. ESA has 3 antennas, and JAXA has some antennas, and we do international cooperation with them, and we're actually able to do handoffs with them also, and also back each other up if we're in the same location in the same view.
Well, in addition to upgrading the technical capabilities, which we heard about from Amy, are you guys upgrading? I'm leading you somewhere because you're also operating the operational capabilities, though. I mean, can you talk a little bit about some of those? And you helped to develop this one really interesting follow the sun idea as well. Can you talk about that?
Yeah, sure. Happy to talk about follow the sun. So what is this thing? Well, first of all, it is operations. So, operations is very important to our organization. All the technology that Les talked about and the antennas that Amy talked about, if we can't operate them, there's no joy, right? There's no happiness. The missions are not getting their data. So operations, first and foremost, is an important part of our organization. So to understand this follow the sun thing, it's good to go back, say, 50 years when in operations of the DSN, people were dialing in these frequencies on receivers and transmitters. You remember dialing in our radios, right? So 50 years ago, we were doing that in a deep space network, dialing in these frequencies. If you fast forward 25 years, now everything's computer controlled and digitally controlled, and we have networks. And so we're able to take all that operations, which was at every receiver and antenna, and consolidate into what we call the signal processing center. And that's when you see, the typical operations room, where everybody's around and it's kind of the dark room. And so that's 25 years ago. And so today we just had our first anniversary of Follow the Sun operations. That was on Monday, our first anniversary. And so we're pretty excited about that. And what Follow the Sun is about is taking advantage of that equidistant distribution of our sites around the globe, where we can do day shift only operations of the entire network. So we're now interconnected with very reliable networks, high-speed, wide area networks, fully redundant and diverse. And so we're taking advantage of that by controlling the entire network from one location during the day shift. And so, for instance, right now, it's daytime in Canberra. Canberra is controlling an entire network. Later tonight, about 11 or 12 o'clock tonight, they'll hand over to Madrid. They'll control the entire network. Tomorrow morning, about 6 or 7 in the morning, they'll hand over to Goldstone and they'll control the entire network. And that'll happen every single day. And so there's a bunch of advantages to that for us. One, we eliminated shift work, which is difficult and hard on people. And yet we kept the resiliencies of our 3 sites working. And in fact, we're actually can control from the JPL darkroom here, if you've ever seen it for the very first time.
So just to amplify this, Mike and his team have done such a good job at increasing the efficiency and the automation of the Deep Space Network that we've saved enough money that that's actually what funds all the new antennas that Amy's building.
Nice job. So then are there any other next steps in operations that you guys want to talk about? Or?
Yeah, I think the next step for us is really completely automating tracking passes. And we're not going to remove operations from the equation, but we think that reducing that workload and stress of operating through automation is very important. And what we're going to do is adopt techniques that were really first discovered and researched in autopilot systems, and it's called human autonomy teaming. It's now gotten a lot of more press with autonomous driving and things like that. So we're going to use these techniques of, pairing operations with automation and getting the right teaming relationship there, and that involves things like trust and knowing what the automation is doing as opposed to what you should be doing. And that's our future in the next couple of years. We hope to do that.
Well, so one more question from me, and that is, you less talked about using the DSN for science. How do you guys look at DSN's role as essentially a giant scientific instrument? Because I know there are a lot of missions that think of your antennas as sort of an extension of their spacecraft that's just millions of miles away and weighs tens of thousands of pounds. How do you guys feel about that, being kind of part of a mission?
Oh, that's just part of the job, and who wouldn't want to be part of these missions after all? It turns out that almost every spacecraft that goes into deep space does DSN science, just about every one. At least radio science, at least the kinds of things we talked about, interrogating the rings and atmospheres and so forth. There's always something. Even as New Horizons spacecraft passes its first Kuiper Belt object in January, it will be doing radio science to learn something about that body that's so far away from Earth. And it's exciting to be part of this, not just part of the engineering team, but part of the science team.
Yeah, and I'll add, in any communications, there's at least two parts of it, right? There's us, the DSN, but there's the spacecraft part of that communication. So, that's pretty critical. And we try to optimize that communication as much as possible, push the envelope to get as much data as possible. So that does make it more difficult when you push that envelope. And if you go to the museum and here in the room, you'll notice none of these spacecraft are the same. They're going to different places. They're built uniquely for that environment, and they're pushing the envelope of that environment. And so each one of every time we talk to these spacecraft, it's a bit of a challenge. And especially when you're doing things like initial acquisition during launch, or you're going into orbit around a planet. There's no better thrill than getting that signal down from the spacecraft. It's really...
There are times that we do science even without the spacecraft.
Yes.
And one of the things that we do, we haven't talked much about so far, is using the DSN as a radar. And we have very powerful transmitters, we have very sensitive receivers. And so we have, over the years, done radar observations. Sometimes the first glimpse of something comes from the DSN. The first glimpse of the surface of Titan came from the DSN until we got the Huygens spacecraft there and Cassini. We've done a lot of work lately on asteroids, particularly asteroids that come close to the Earth that might pose a hazard to the Earth someday. It turns out that although they're discovered with optical telescopes, if we can just do a single DSN radar observation on them, we learn a lot about the structure and shape and so forth of the object, but we also can predict its trajectory hundreds of years into the future based on those observations. So we get a measure of confidence that, no, we're not going to be hit at least in a couple of centuries.
Cool. Yeah. Well, I think that's a good place for us to stop talking to ourselves and hear from you guys. So we'll take your questions if you'll step to the microphone that's in the middle of the room, in the middle of the aisle there. And also we'll work in a few questions from folks watching online. So step right up there and go ahead with your question.
Hi. What you guys were talking about with having really powerful transmitters, both on the ground and on the spacecraft. Like I myself actually work with radios a lot, like portable ones that run off of AA's and 9 volts and can go like 100 milliwatts, sometimes up to 250 milliwatts. So I'm wondering, to talk to something like New Horizons or Voyager, like what the wattage, because I'm sure it's not milliwatts, of what the wattage is for the ground transmitters, and what wattage you have to put in the spacecraft to talk.
It turns out that, so it turns out that Voyager uses a unique transmitter within the DSN. We only have one of them left. It's located in Australia. It is a 400 kilowatt S-band continuous wave transmitter. So yes, it's a lot bigger than the ham equipment. But the typical transmitters we have are between 20 kilowatts and 80 kilowatts.
Nice.
Yeah, and on the spacecraft side, you're talking about, 10, 20 watts.
Okay.
Power's
That's
much
still
more
amazing.
limited there.
Yeah.
That's still amazing. You can get it to go that far, up like 20 watts.
Yeah, that distance squared is really tough,
all those
especially
techniques we
when it's
talked about.
20, 40 watts from spacecraft.
Thanks.
Regarding the issue of telescope array, you mentioned the delta difference measurement. What about the idea of putting a distance between the antennas, put one here on Earth and another one on the moon, where the moon is actually face locked to Earth? So is it feasible, possible? And what do you gain because of this enormous distance between the two antennas? And another question, if I may, if you can make some comments about the internet protocol for space.
Okay, I'm trying to remember both of those. Okay, so the first one, the same technique that we use for delta Dor, when it's used in astronomy, it's something, they call this very long baseline interferometry, but it's basically the same kind of mathematics. So although we don't need any more accuracy for navigating the spacecraft than antennas that are a few miles apart, to do certain kinds of science observations using that technique, you want as large a baseline as you can. And we do this in the science sense on an intercontinental basis today. We can do more than that. We have flown, there have been a couple missions flown, a Japanese mission in particular, that carried one antenna with the other antennas being on the Earth, and it was a high Earth orbiter. And so it provided that large baseline, not all the way to the moon, but getting close. When we get to the point of having infrastructure on the moon, yeah, we have already talked about could we have DSN-like stations on the moon, and what could you do with them for things like this? So absolutely, we're looking at that. Your other question was about internet protocols. Okay, it turns out that we don't use internet protocols in deep space because two things break. First of all, the internet protocol suite that we use here on the surface of the Earth cannot work over those kinds of delays in terms of how, the speed of light times the distance. And they're just not designed to work. That's an easier one to fix. But the other problem is, on the surface of the Earth, when you are, for instance, accessing this live stream from your home, there may be 20 servers in between here and there. Every one of those links has to be active at the same time for you to get your video in your home. We can't do that in deep space because, for instance, as the Earth turns, one DSN site goes out of view and the next one comes up. So if you're orbiting a planet, you have the same problem. The planet's going to get in the way. You need a set of protocols that can handle both the long delays and the disruptions in communications channel. There is such a suite. It's called DTN, or Disruption or Delay Tolerant Networking. We're doing research on it now. It exists operationally on the ISS, on the space station today, and we have plans to introduce this into the DSN in the next few years.
Thanks.
Yeah.
Hi, two questions, if I may, with regards to the optical communications upgrade. The first question is, when dealing with optical propagation, that there'll be problems with atmospheric interference, such as clouds and rain and so forth. How do you plan on addressing that? Are you going to use redundancy of the other stations? The second question is with regards to utilization of the beam waveguides. Will you have to down convert to microwave to implement the mirrors as designed, or will you propagate directly using the optical frequencies? Thank you.
So to answer your first question, it definitely is dependent on weather. So that's why we'll be developing and delivering the first system at Goldstone, which is out in the desert. It's very dry. We don't have to worry too much about clouds or weather. And at the moment, we're actually studying the other sites and looking at a whole host of years and years of weather data and analyzing it to figure out where the next site would be optimal to deploy an optical system.
And to add to that, we're actually looking at the average increase that optical communications give you, and that includes the outages from bad weather. and depending on where your site is. Even if you have those outages, if on average you come out better because when the sky is clear, you get so many more bits per second, you're still better off doing this as long as you have an automated way of handling that link, and that same set of protocols I talked about serves that purpose as well, to automatically pick up whenever the weather is good again and get the link going.
Thank you.
You had a second question.
The beam waveguide implementation.
Yeah, so even though we're going to be putting these optical systems on beam waveguide antennas, we're not actually using the beam waveguide in the optical system. That's why we're putting the optical receiver at the apex of the antenna. The idea is it doesn't then come down through the waveguide, it goes electronically off of the apex. And we looked at both designs. We did a trade-off and decided this was the better design.
Let's take a real quick question from YouTube. Jeff on YouTube wanted to know, how do solar flares affect RF signals from spacecraft?
So I talked about the T's that you can't control. So that's a noise that we have no control over. It turns out to be temporal. It's not there all the time. It comes and goes. It does affect the communication system. It can affect the communications directly by affecting the electronics in the DSN or on the spacecraft. It can affect stuff that happens in between. Currently, if we know about flares in advance, we turn spacecraft off just to protect them so we don't communicate. But otherwise, it's just another one of those T's, and we have to have enough other communication sessions to make up for it.
Yeah, it's a little less about signal disruption than it is about the electronics being disrupted, because it's different frequencies typically, although it is present in the T factor, as Les points out.
So I'm really inspired by this gorgeous model of Voyager over here, and I've been really curious. How much longer do you think we'll be able to communicate with the Voyager spacecraft, and what data are we actually getting back right now?
So we're actually getting back very important data from Voyager, from both Voyagers, but from Voyager 2 right now, because it is about to cross the heliopause. So Voyager 1 left the solar system a long time ago now, but we've purposely sent them in different directions so that we can see somewhat of the shape of that boundary. And Voyager 2 is about to go through that. So that's an extremely important science result that's coming from a 40-year-old spacecraft right now. We still get measurements of magnetic fields and particles and so forth from both the Voyagers. And that's our only probe into interstellar space at the moment. That's how all we know about it is coming from Voyager pretty much. So in terms of how much longer, we're trying to keep them going as long as we can. And
I think the latest I've heard is around 2027.
Yeah, that's correct. Yeah, at some point there's not enough power to operate both the transmitter and the instruments and the heaters that keep these things alive.
Since we're talking about Voyager, we actually got two questions from the webcast viewers that relate to it. So I'll go ahead and slip them in here now. Are you seeing any gravity science signal from the Voyager as it's leaving the solar system and going away from the sun's gravity? This is from Virchi on YouTube. Any noticeable effects of gravity on signals?
Unfortunately, we don't have Voyager scientists here with us. I don't think we do. I think what we're mainly looking at is fields and particles data and looking at the difference as Voyager traverses different regions at the outskirts of the solar system.
Okay, and then Shub on YouTube wanted to know do you have an estimate of how many bits per second we get from Voyager? What's the Voyager signal like in terms of data?
I think we're getting up to 1,200 bits per second.
And how does that compare to something like Juno or Cassini?
Mars Reconnaissance Orbiter orbiting Mars is 6 megabits per second. We have Earth trailing missions, TESS, for instance, 125 megabits per second. So there's quite a variety of data rates for the different missions.
But 1,200 bits per second isn't zero. It was what we did on modems 30 years ago for our own computers. And it's enough, for instance, to transmit encoded voice. You can have a human on Voyager and listen to them.
We're so spoiled with data rates nowadays, aren't we?
Yeah.
We are.
Okay. Hi there, how are you doing?
I remember from the old days when Dr. Pickering and Dr. Ebrechten and Dr. Andrew Viterbi were working on the Deep Space Network. And I was a student at that time, and we're trying to figure out what is going on. We're learning this thing. For over these years, you guys have done magnificent job. Can you briefly tell me from point A to what is happening now, what has happened over this period of time?
Briefly? It's all that. It's
Some
that
data compression.
yeah. So it was that 10 to the 13th curve. If you look at all the JAGs on that 10 to the 13th curve, each one represents a new technology or a new capability that came in. Andy Viterbi, you mentioned. At some point, we went to convolutional coding using maximum likelihood decoders, which other people call Viterbi decoders. And that went in the late 70s, I think. Irving Reed, maybe Irving Reed, Gus Solomon. Those codes came in the mid 80s. So, I mean, all these people you're talking about, Ed Recton is the architect of the DSN. He's responsible for how it looks in the overall concept. So all these people contributed.
20 years ago, they were sitting here in the same place and talking about the deep.
Well, I've had the pleasure to talk to some of them about this over the years. Yeah.
All right, thank you.
Yeah.
Okay, thanks.
Yeah, you had a question a while back about the effect of weather on the optical navigation. I assume you're using infrared. Is it far infrared or near infrared?
The standard that we've developed is 1550 nanohertz. No, sorry. Sorry.
I think not.
There's too much microwave in me.
Nanometers.
Yeah.
Yeah. Several years ago, I heard a rumor that there was a consideration of actually using internet protocols among the spacecraft that are currently orbiting Mars. Are you using the delay-tolerant networks there, or are you using internet protocols there?
We're not using either of those protocols at the moment. We do have a proprietary sort of international space protocol that we use for relays at Mars. It's neither of those, but in the future, we expect DTN to be implemented there.
Yeah. The final thing is just a little remark. Did a quick calculation as I was standing here. The data rate from Voyager is 15 times the data rate from Mariner 4.
Yeah. There you go.
Take that, Mariner 4.
Yeah.
Hi. Someone mentioned earlier that you get the ability to communicate with 4 spacecraft simultaneously in one place when they're conveniently located like that. Adding sort of the optical wavelengths, I'm imagining that's not just going up by 1 using different frequencies. You just mentioned 1550, but are you using different frequencies or different ways to encode that so you can get more than 4 simultaneous communications?
So I think Mike mentioned that at radio frequencies, we actually, although they may all be at X band, which is like 8.4 gigahertz downlink, they're at slightly different X bands, so they're separated in frequency space. At the moment, we haven't thought too much about multiple optical spacecraft in the same beam because we don't even have one yet. But we will be thinking about that. And there are people working on either wavelength diversity or code diversity. The various techniques you can use, and we haven't decided on the right one yet.
Cool, thank you.
Yeah.
Hi, forgive me if my question is a bit of a stretch from what we're generally looking at right now, but in my physics class, we're studying the fuel sources that we can use as a society. By any chance, do you know if the main fuel source that's powering sorry, I forget the word, I'm a little nervous right now, but the main systems that we're using right now to get the signals from the outer space missions that we're sending?
Okay, so most spacecraft have solar power. And the exceptions are ones that are too far from the sun, so there's not enough solar flux to generate. And those are carrying small pieces of radioactive material that generate heat that's converted into electricity. So that's what's in space. On ground, we mostly use commercial power. And so it's not our choice as to how the power is being generated. It's locally what's available in the 3 countries, in the 3 places. We have, over the years, looked at installing alternative energy sources at the complexes. It's still under discussion.
All right, thank you.
Yeah.
We got another question from David on YouTube. He wanted to know, do the antennas communicate in duplex mode, or do they switch back and forth from transmit to receive? Can they only do one thing at a time, or can they do them both?
No, they can do them both or one at a time. So we have different modes of operating. So there's one-way mode, which is we typically call downlink only, as we see it from the ground side. We have two-way mode where we're uplinking and coherently turning that signal around on the downlink. So that's downlink mode. And then we also do two-way non-coherent, which the turnaround ratio is not used on the spacecraft. So we have an uplink and a downlink. So
You may ask why we have so many modes.
Right.
And one of the reasons is when you operate in a full duplex mode, the performance goes down slightly.
Right.
And so if you're trying to get the last possible bits per second out of the spacecraft, like you have an encounter with the planet, you're trying to get as much data down that day as you can, you'll go to one-way mode because you pick up a little bit of performance.
Hi.
Hi. You had mentioned earlier that you might use these satellites to help get the shapes and of distances of asteroids in the field. I'm curious to what sensitivities do we have for the resolution? Like how close can we get to the size and of a particle or whatever?
Yeah, so that's really a question about the DSN being used as a radar. And it turns out that the distance isn't what affects the resolution. It's the bandwidth of the signals, how much frequency bandwidth there is in the signal. And we recently, maybe 4 or 5 years ago, upgraded our radar system. We get about 4 meters of resolution on these objects. So a pixel is about 4 meters.
Thank you.
Thanks. Hi there.
Hello. I think we're mostly all aware of the fact that we can't change the distance of the spacecraft to the DSN, and that we can't necessarily increase the fastest speed of the data coming through. So I was wondering what steps are being taken to increase the effectiveness of communication for the crewed missions going to Mars in the 2030s and 2020s. And also I heard a brief mention of artificial intelligence within the DSN. I was thinking maybe you can elaborate on that.
So let's take the astronaut question first. So the DSN was involved in Apollo, and we were also involved in the shuttle program, particularly when it used to land on the West Coast. We were part of the landing sequence for the shuttle. But since then, the DSN has not been involved directly in supporting astronauts in space. So we're very excited with the return of American astronauts to deep space, which will happen in a few years. And so we've been working toward that for a while. We've installed in the DSN the different kinds of communication standards that those missions want to use. And so we are completely ready to support the first foray, which are the exploration mission sequences, starting with EM1, which is not piloted, and then EM2, which is. So those will happen over the next few years. Then, of course, the next thing is the Lunar Orbiting Gateway, which NASA is now designing. And we've been involved in helping define the communications architecture for it, because the DSN will again be the main link to that. As far as Mars, we've been working on Mars for quite a while. In fact, one of the reasons that we're very excited about the optical communications and the beam waveguides is that will likely be the way we communicate with astronauts at Mars.
in terms of AI, we have some AI algorithms in our scheduling software, which I talked a little bit about, which is based really on temporal dependency networks and kind of construction algorithms to construct the schedule and repair algorithms when there's some breakage in the schedule. And then we're also looking at machine learning for doing things like situational awareness. So like as we move into more automation, we're also going to automate some of the monitoring functions. So we're using machine learning to ingest a lot of data to understand relationships between that data and detect errors or faults as they're occurring or before they occur, and kind of warn operations that you ought to pay attention to this or that when we're in a more automated mode of operating.
Well, are you guys going to build any more of the really big antennas, the 70-meter, the football field size ones, to help communicate with astronauts, or are you guys going to just keep building the 34 meters that Amy talked about?
So at the moment, we're building 34s, and the reason for that is we actually did a study a while back and said, if suppose we need to have that much more area in our antennas, what's the most efficient way to do it? If you go back far enough in time, the only way to do it was with one big one. But now we know how to array these together. And so now the question is it better operationally and economically to build one big one or a set of small ones? And if it's a set of small ones, what should the diameter be? Should they be a bunch of 34s or a lot more 12s or a whole bunch of 6s? And we did the trade-off study, and it turns out that at the time we did it, which was a few years back, and for the kind of extra aperture we wanted, which were the equivalent of 6 of these antennas, 34 meter was the right answer. I expect as technology advances, that number will go down. And so if you come back and ask this question of this panel 20 years from now, we may be building 10-meter antennas for our arrays.
Thank you.
Yeah.
I was just curious as to where all of the antenna hardware is built and how do you get it shipped out to the 3 sites?
Yeah, so it very much depends on what it is. So generally the electronics are developed and built here at JPL. I mean, we have some pieces that are bought from industry and then assembled here and tested at the system level for our electronics. But things like the steel structure is bought locally. And the panels are also, the panels and subreflectors for the antennas I'm building right now come from Italy. And so it's a combination, but most of the electronics are developed here at JPL.
Is there a problem with shipping? I mean, do you have...
So what we end up doing is we pack all of our electronics into sea vans, so big 20-foot or 40-foot sea containers, and then we load them on a ship, and they ship across the ocean, and then they get unpacked over there. So, for example, for one of these antennas, there will be 4 to 6 20-foot sea vans full of equipment that will be shipped over there. So it is, it's like a game of Tetris, right? To get everything packed in there safely so that any sort of movement, all of the movement in that sea container doesn't damage anything, but we get kind of an efficient use of space.
And we have a whole logistics operation that's done by our American contractor, Peraton. And they take care of the logistics for this. They have depots for managing inventory and all the stuff that goes along with a modern operation like this.
Okay, thank you.
So here's a question from Ethan on YouTube. He wanted to know, Ethan wanted to know if we're planning anything to do with quantum communication satellites. I don't know, maybe that is related to encryption or encoding data?
So when people use the word quantum in communications in the same breath, it could mean many things. But we are doing research in quantum communications. It's one of the things that we might go to for the next step of performance improvement after optical, for instance. And when I think of quantum communications, what I'm thinking of specifically is 2 things. 2 things I'm thinking specifically. One is taking the photons that we would transmit over an optical channel and not just measuring whether they exist or not, which is what we're going to be doing in the first generation, but looking at their states and carrying information in the states of the photon, not just the presence or absence of the photon. That's classical quantum communications. Then there's stuff like quantum entanglement. The idea is if you pair photons at the source and force them to synchronize their states and then move one to the destination, then you can change the state of one and see the change occur at some point on the other one as well. And we are doing research in that. There have been demonstrations on the surface of the Earth. The Chinese have put this in orbit. I haven't seen the results yet, but it's very promising. At some point, somebody's going to make this work. And we are definitely following this and investing a small amount of our technology money to understand it so that we're ready to take advantage of what comes there.
Would that get rid of the D, the problem of the D that...
No, unfortunately.
Instant communication?
Yeah, none of this is in conflict with Einstein's theory yet.
Oh, well.
Yeah.
Hi.
Hi. Is it possible that long-term constant communications with these deep space spacecraft could potentially alter their trajectories, like similar to a solar sail?
So yes, it is. At the levels that we transmit to the spacecraft, you'd be hard-pressed to measure that difference. But if you have a large enough collecting area on the spacecraft, you say a solar sail, and you transmit with a large transmitter from the Earth, you will be able to move it. And in fact, there are designs for demonstrations of that technology. We haven't done it yet, but that's something we could do with the DSN, is demonstrate if we can put a solar sail out, that we can actually change the trajectory of the spacecraft with a transmitter from the Earth. But it's absolutely, that does not violate Einstein either. Yeah.
Hi. So is there a specific reason why those three locations, like Madrid and Goldstone, were chosen to build the antennas, or is it kind of just because of convenience?
Yes and no. So from my first diagram that showed the view from the North Pole of the Earth, you want to have things that are about equidistant around the Earth, and that's just operationally, so there's something always in view. But you also, there are a whole bunch of other things. You want to be in a place that has reasonable weather, that has a good workforce, intelligent people who can operate the antennas for you, that is politically aligned with the US policy-wise. Understand, like for instance, when the DSN was new, we had an antenna in South Africa, but when apartheid went into effect, we moved that complex away. So politics does come into play. So all these things, one of my friends at headquarters says there's science and there's political science. They're both valid. Yeah.
Okay, thank you.
Yeah.
All right. Well, I think unless there are any other questions, then I think that's all we'll talk about tonight here with regard to the DSN. So thanks to all of our speakers and to all of you for being here. Thanks to everyone who's watching online as well. Our next show is on January 11th, so join us right here for our celebration of 50 years of exploring Mars. We'll see you then. Good night.